Hello, and welcome to another 8 bits of video. This time we're going to be looking at different parts of the Visual Studio debugger you should be using. It doesn't matter how good a programmer you think you are, eventually you're going to need to debug something. And if you've watched any of my videos, you know that I'm quite a fan of the Visual Studio tools, and they've got some very powerful features that can really help you debug your code. The 8 bits in this video aren't in any particular order this time, but should be enough to give you a good understanding of the debugger's capabilities, so you can experiment for yourself. Let's get started. I'm sure if you've programmed in Visual Studio, you're quite familiar with how to compile and run your program. And if you run the debugger, your program runs and exits, and we get some output, and you might have a little console window or a logging facility which you could have used to capture what your program has done. However, sometimes it's a lot more useful to just look at your programming running in real time. Now you may notice I've popped a little keyboard on the screen, and this is to show you some of the keyboard shortcuts that I'll be using in Visual Studio. With any debugger, the first and most important part is actually getting to the code that you want to debug. You don't want to start from the very beginning of your program every single time. So I like to press the cursor where I want it to be, and then press the Control and F10 buttons. And as we can see, the debugger has started, and this yellow arrow here indicates what line of code is about to be executed. Let's take a minute just to set up the environment to something useful. If you go to the debug menu up here and select Windows, the things that you'll want to see are the autos, locals, the call stack, possibly the threads, and a memory window. You want at least one memory window. That's enough to get started. So knowing that Control and F10 will start and run to a location, just pressing F10 on its own will execute it line by line. Let's first have a look at the locals window. The locals window will display all of the variables that are in the current scope of your program. Now my program only contains int main, so any variables I've defined are all local. And we can see here for this int a, it's up here and it's currently not got a value. That's because of course it's not been defined yet. This line of code has not been executed. As soon as I press F10, we see that a has assumed the value 7 and it recognizes it of type int. Press F10 again, and we've executed the next line now, where value b has been attributed the value 8, and it's a float. And so forth. We can see, as we step through the code, these update themselves automatically. When we use a more complex type, but something well established within the C++ language, like a string, the debugger also actually makes it quite useful to see what the contents of the string is. So we know that behind the scenes a string is effectively a linked list, but the debugger is intelligent enough to tell us, actually, it's a string, and the value of the string in this case is hello. By selecting the arrow next to the S here, when it's a type string, it can be expanded to show what the string consists of. So we can see its size, we can see how much memory has been allocated to representing this string, and we can see the individual elements here in the container. This hierarchical way of looking at data is quite common in the debugger, and it will do the same for structs and classes. This of course is a different way of storing a string. If we just allocate a buffer directly, we can see up here the buff has been allocated as an array, including the escape character. This is the debugger being quite clever, and it recognizes that buff is actually a char, and it will just keep displaying the data associated with this char pointer until it reaches the escape character. Another powerful yet potentially dangerous feature of the debugger is you can edit the values of the memory. So if we wanted to change the value of integer a, which is currently 7, to something else, let's say 3, we just double click on it and set the value. And that's it, it's done, it is now 3. Even though in our code it's quite clearly 7, and we haven't done anything to set it, but we have changed it behind the scenes. Sometimes another useful thing to do is to set this to hexadecimal display, where we can see the hex equivalents of the values. This may look untidy at first, but later on if you're starting to work with bit strings and bit arrays, this can be quite a useful tool. Leading straight on into bit 7, we can see how pointers are also handled by the debugger. Using the variables I created earlier, I'm going to create a couple of pointers to those variables. So in this first line here, I'm creating an integer pointer to the variable a. If we have a look in our debugging window, we can see that PA here is currently undefined. That's the 0xCCCCC. I'll just pop this back into decimal view. And we see here some curly brackets with some question marks in. This is the debugger telling us what the value is at that pointer location. And it's currently undefined. So let's define it by stepping to the next line of code. We can now see the pointer has been given a memory address and it contains the value 7. And this is where having a memory window can also be quite useful. We can just click and drag that address into the memory window and have a look at it directly. And we can see, of course, up here in the first element is our 4 bytes representing the integer, and its value is 7. If we wanted to, we can change the value of this memory by right-clicking and selecting Edit Value. Any memory that changes gets highlighted red, and we'll see a bit more of this later on. Let's have a look now at the floating point pointer. We can see the debugger knows what type it is and displays the data accordingly. If we have a look at this in a memory window, this is the hexadecimal equivalent of our floating point value, which of course doesn't make much sense to mere mortal humans. So to make this more readable, you can right-click and choose a particular data format to display. In this case, I know my floats are 32-bit floating points. So I will change the memory display to 32-bit floating point, and we can see the first value is 8, which is the actual value that the pointer is pointing to. Let's put that back. If I press F10 again, we've now given the pbuff something to look at. We've given it the value buff, which was our character string before. And as you might expect, there is little difference between the buffer created here and the pointer to the buffer created here, because they are one and the same. But if we drag that over to a memory window and have a look, we see there's some hexadecimal characters here which represent our world, and it actually shows you that in the memory with an ASCII interpretation of the hexadecimal characters. Bit 6 is about navigating functions using the debugger. So if I control an F10 to this line, it's executed all the code that we saw before, and we can see where we are in our current call stack. At the moment, we're just in main, highlighted by the blue line up here, and there's a little yellow arrow telling us where we are. Now if I press F10 again, what's going to happen is I'm going to step over that line. It has executed the line of code, and we can verify this by looking at the local variables. It says up here, function 1 returned the value 49, which if we go and have a quick look at function 1 by expanding it, we can see it's just the square of whatever the argument was. However, what if we wanted to debug function 1? Well, we have two approaches. The first is we can select a line in function 1 that we want to debug and press Ctrl and F10. Of course, our program will run to that line. And if we have a look at our call stack, we can see main was the original function that was called, which is here, and we've now called our function 1. Once we're inside this function, we can press F10 to step through the code as normal. And when we get to the end of the function, pressing F10 again will take us to where our program currently is up to. The second way to debug the function is to Ctrl and F10 to it, and you can now press F11 to step into the function. And back out. Stepping into and over functions and any other kind of call in your program is vital to debugging, as there's pretty much always a one-to-one relationship between the nature of how you're stepping and the order of the program execution. However, this is where things can get a little bit daunting. Let's say I control an F10 to this string declaration. Well, of course we know that string is actually an object, it's not a primitive type. So if I press F11, I start to step into the constructor of the string, and as you can see, it gets quite complicated. If I start stepping through this code, we can see how everything works. But I'll be pressing F11 for a long time here, so sometimes I need to step out of the code. And to step out of a function, it's Shift and F11. So hold down the Shift, hold down F11, and eventually I get back to where I was. The code is still executed even though it's called stepping out. And now I can just press F10 to carry on as normal. Bit 5, breakpoints. Breakpoints are a very traditional way of debugging, and for Visual Studio you can set a breakpoint by selecting the line and clicking somewhere to the left here, and we set it like a big red circle appears, and this will tell the running program to stop when it gets to that code. So I'm not going to press Ctrl and F10 this time, I'm just going to run it. And we can see where the yellow arrow is, where we're up to in our execution. It's stopped at the breakpoint. I personally don't tend to use this very much and I prefer Ctrl and F10. However, it does have some useful advantages. Take this code for example. I have a little for loop that's doing something repeatedly. But let's assume I discover a bug where something only starts to affect the program when I is equal to value 55. I could sit here now pressing F10 and monitoring the variable window up here and monitoring the value of I until it is equal to 55. I'll be here all day. Instead, what I can do is set a more intelligent breakpoint. So I set a breakpoint and click on the little gear next to it, and the condition I'm looking for is that the breakpoint is only active when I is equal to 55. Let's close the window and run our program. So the program has stopped. If I put my cursor over the I value, I can see, yep, I is 55. That saved me quite a bit of time. But what happens if I don't have a value to break on? One of the things I can do is say, please only break once that breakpoint has been hit a certain number of times. So to do that, we go into the breakpoint settings, choose a condition, and we can choose hit count. So when this particular line of code has been executed, say 55 times again, and we run it, we can see the breakpoint has now been hit on the 55th iteration of this loop, where of course i's is 54 now, but that's okay, I'm close enough, I don't mind stepping through a couple of lines. Bit 4, parsers and visualizers. Now this is quite a modern feature of the Visual Studio Debugger, and I'm sure this is a section of it that's going to expand in the future. But Visual Studio now contains ways of displaying more complex data types. So in here I've created a string which contains some HTML code, so it's just the body and a link, and I've also got a JSON object, which I've pinched from the JSON website, from their example page. And yes, they look quite terrible, but it is a popular way of manipulating data. Let's see how the debugger handles these. So I'm going to Control and F10 to it, and we'll look at the HTML one first. So we'll find our variable. At the moment it's not been defined as anything, but as soon as I click on here, we can see it's just a string for all intents and purposes, but right next to it there's a little magnifying glass. And I can choose how I wish to visualize this string. And if I choose the HTML visualizer, it actually displays HTML. And this is the link that we created. In fact, it's so good, I can click on the link and it takes you to my website. This isn't a fully functional HTML browser, but it's good enough. A similar thing happens for the JSON object. The JSON object now contains a string, so let's have a look at that using the JSON visualizer. Well, as you'd expect, it breaks it up into the tree. Frustratingly though, it doesn't actually let you edit anything within the JSON object. Maybe that'll come in a future version. In fact, I'm quite sure that as development of the Visual Studio Debugger continues, we'll see this list grow and grow and grow with lots of common data types. Bit 3, edit and continue, and this is where we're going to start really breaking our programs and doing lots of dangerous debugging strategies, but you'll never know, they might just help you out occasionally. Here I've got two identical lines of code. I'm calling my function with the same argument and just giving it to a different variable each time. Well, if we look at the code for my function, we can see it simply squares the value and returns it. So for the first value, I'd expect 36. I can put my cursor over A1 here and we see of course the value is 36. We can validate that by looking at the locals window. Just point out the autos window at the moment is like a summarized locals version, so the debugger has decided what useful information do I need to see. In large programs this is invaluable. But this is where we can exploit a really powerful feature of the debugger. I can now go and change the contents of my function. Let's make it cube the number by timesing by t again. This time when I press F10 to step through the line of code, it compiled, it said here, edit continue successfully applied code changes. And if we have a look now, A2 should be the cube of 6, which indeed it is. I think this is really clever. We've changed the executable code of an executable whilst it's running. There are some caveats to this though. As your programs get more complex and contain threads and classes, this will stop working and the compiler will tell you that it can't apply the code changes without needing to restart your program. It's also important to remember that you have now changed your source code. It won't revert back to the original form when you stop debugging. So I stop debugging and go and have a look at my function. It is indeed now the cubic version. Bit 2, performance monitoring. Have you ever wondered what this really annoying window is on the side that keeps accidentally popping up when you're running your program? Well, it's actually quite a useful tool. If we enable the CPU profiling button here and run our program in debug mode to a line, Control and F10 here, and then go to Debug, Show Diagnostic Tools, what we're presented with is how our program has used the processor and the memory. Here on the left we have the function names. Now most of these will be part of the Windows runtime, but if we dig in deep enough we can see in our loop that the bulk of our CPU time was done calculating the pow function and some was done calculating theatan function. This can be used to indicate that perhaps this function needs to be more optimized. Admittedly, the names of things in this window are a little cryptic, and I would say that if you're just starting out, don't worry too much about making your code super fast. Focus on making it work. And finally that leaves us with bit 1, memory leaks. I guarantee if you want to be a C or C++ programmer, you will face memory leaks at some point during your programming career. Let's take this first example where I have created a buffer 1 on the stack, so everything is known at compile time. And let's see what happens when I run this program. Of course we get runtime check failure. Stack around the variable buffer1 was corrupted. Let's see if we can work out why. At least it's given us a hint that it's something to do with buffer1. The way I would debug this is to stop the program and control an F10 to the start of it and have a look what we're doing with buffer1 in order to corrupt it. Well, if I take the address here from buffer1 and have a look at it in a memory window, I know of course here that buffer1 can only contain 5 bytes. Let's see what happens as we step through the code. Well, the first one got written there, value 0. Second one, 1, 2, 3, 4, 5. But my program keeps going. It's writing to memory that it doesn't have access to. And the debugging environment will be able to check this later on. It knows that if these values have changed, and they shouldn't have done, then we've done some kind of corruption. The situation sadly only gets worse when we want to start dynamically allocating memory. So in this case I'm creating 5 bytes of space on the heap. And if I run the program, no problems at all, even though I know bad things just occurred. Let's control F10 and have a look. So if I find my buffer 2 here, it's not been allocated yet, let's press F10. Buffer 2 has now been given an address. Let's drag that onto a memory window. And we can see that the new function has created memory but given it the value CD, 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 and this one up here is the 5th byte. That's great. In debug mode, memory around this location will also be set to FD, FD, FD. And as we run through our loop, we can see the CDs change quite nicely. There's our 5 bytes. But it'll quite happily let us write the next byte. And this is because in debug mode, you've got this little bit of buffer to keep things safe and stop your program just being terminally crashed. This doesn't apply in release mode. On the whole, memory leaks can be a real pain. There are strategies to try and catch them. You can override the new operator and the delete operator, and you can use smart pointers and other tools provided by third-party libraries. However, vanilla Visual Studio doesn't provide you with many tools to help you get through this. So there you have it, a very brief look at the basic tools provided by the Visual Studio debugging environment. I think it's really important to use these tools to your advantage. The debugger also includes tools for debugging multi-threaded applications and multi-process applications, but I think we'll leave those for today. If you found any of this useful, give us a thumbs up, have a think about subscribing, and I'll see you next time.